Hello friends, this is me from the future. Before starting, I would like to give you some interesting sources, in my opinion, to tackle the problem, because I realized that while I'm coding, I don't go too much into details. So the first thing is this Medium article that I wrote about the dynamic philosophers. It contains the functions that I used in my code. For example, the precise, use lib, and other things. Basically, I go into the details. You can read this if you want to dig down, if you have any doubts. Basically, these are my notes, the notes I took before tackling the dynamic philosophers, so you can have a check. There is also a video here. So this is all the theory I needed to code this thing. Of course, I have another article related to deadlocks, again with the video. The deadlock is the gist of this dynamic philosopher. You need to avoid this. So here I wrote as well my notes with some code to test, and that's it. Then I would like to mention this blog by Mia Combo. Sorry for pronunciation. J'ai oublié le français de cette façon-là. Voilà, Mia Combo, je pense. Voilà. Excusez-moi. And this blog is really amazing, especially for threads, mutexes, and concurrent programming in C. But generally speaking, it is a very good source for 42 school projects, C programming, and computer science in general. So kudos to Mia, amazing source. Highly suggested, especially this one for the dynamic philosophers. Then there is also this video here from, good luck, where are you from, my friend? Russia, Bulgarian, it seems. This is a good video which gave me a go to the project, so thank you very much. I suggest the guy, follow him, legit. Then, apart from sources to tackle the dynamic philosophers, I wanted to talk to you about a little Notion page that I'm doing on the spare time, in which I basically put all the sources I'm using, I found online. This is a public page, right? This is a public page that everyone can modify. Everyone can basically put its own links here, its own stuff. The sources used to do projects and so on, not only from School 42, related to C programming, to Vim, to Shell, whatever related to computer science. Because I have a lot of people following me, not only from School 42. I know a lot of people follow me from AXL School, which is an African school. Basically, it's a School 42 for Africa, as I understand. So what's the gist of this Ocean 42? Doing that, we can create a big repository that everyone can use and everyone can exploit to find sources, good quality sources, right? Because the thing is that it's very tricky to find good sources, in my opinion. I mean, I get a lot of views from my channel, which initially was thought only for me to train myself, and allegedly a lot of people requires these videos. So here it would be marvelous if we can collect a lot of creators making video blogs and so on related to coding, and they can all share their own page, get exposure. This is not a snake oil link, like link in the description. I want to get the fee from ads. No, this is not. This is just a bare bone Notion public page. I don't sell anything. This is just nothing. It's just a a project that we can do all together, because we all have the same problem. We want to learn how to code for free, so we can crack the code all together. Going into the detail, for example, there is already a girl that made a very amazing lesson for beginners here, variables and functions. It is in French, the girl is French, Elsa, salut Elsa. And basically is this ebook, frankly, very well done for beginners in the C programming language, which is freely available. Everyone can read, can use, and I think this is sick. If we get a lot of creators sharing stuff in this Notion page, we can have a really marvelous repository in which everyone can fetch something, give something. Giving something, you will get exposure eventually if this becomes a thing. So it's a positive sum game, win-win. Everyone wins. You share your stuff, you get followers, you can say you're cool, you increase your subs in GitHub, and everyone is happy. Of course, please don't spam. There is plenty of snake oil sellers in YouTube and in internet in general. So in this page, there will be a garbage collection, not like C. This will be like Java. Here, keeping with the team of creators sharing stuff, I highly suggest to you another simple name, Thagonaut. I don't know, sorry for pronunciation. She made an amazing tutorial for push swap, explained masterfully, much better than me. So I'll suggest to follow the girl and prompt her to make more videos because she is really good. A TLDR would be, we can create a big community of learners who share stuff and everyone wins. We learn to code for free, just for fun. So that's it for this boring introduction. I hope my Dining Philosophers solution is correct, 100% correct. It just works, but I'm not sure that's the real correct thing. So we're gonna do this together. Please comment. And if you want, here's the community. You have the link to the actual Discord and you can come in the server and tell me, hey, your solution is really bad. Here's mine. Boom. And you submit, and we're all happy to have a better solution. Thank you very much, my friend. Hello friends, today is gonna be the Dining Philosophers problem. This is gonna be kinda longish. I will try to code this from inception to conclusion, so you're gonna be able to see how I tackle a problem like that. This is the kind of video I'd like to find on YouTube, so I'm gonna produce myself. Hopefully this is gonna be useful for someone else, and yeah, let's just start. And indeed, this is gonna be a community work. Don't follow me like I know everything, I'm just a dude with a macOS coding like you, a student like you. So there can be mistakes, there can be bugs. This is just my implementation. We do this together, right? Write in the comments if you see some bugs, some performance improvements that we can make and so forth. We are together in this, my friend. All right, let's start. So I initially create my directory, like always when we do a project, Philo, and I cd into it. I will create, like always, an header file. And in this file, we are gonna put all the necessary libraries, all the necessary defines, and so forth. All the jazz that we need to resolve this Dining Philosopher thing. So I'm gonna include stdio.h, this for the printf function. Include the standard library. This is gonna be for malloc and free. Unix standard for the write system call, but we're not actually use this because we have the printf. More important, for the uselib. This is an important function for our project that we are going to use. Indeed, we're going to use uselib with steroids because uselib is not very precise, so we need something better. Include standard bool. Why not? I like to use bools. And then, of course, the pthread.h. Here we have all the functions controlling mutexes and threads. That's the gist of this simulation, right? I have mutex, init, destroy, lock, unlock, these functions. And for threads, I have create, join, detach. Then I have also from the system time.h. Here is useful for the function get time of day. Get time of day. This is basically a chronometer function. It's useful to get exactly the time from a specific epoch, you will see. All right, these are the headers. Let's include also limits.h for int max. We're gonna check our inputs that are not measured in int max. Now we have to model this problem in such a way that a computer can resolve it. A data structure problem. So what is the task on hand? What I'm trying to do? Well, the Dining Philosophers problem, as you probably already know, is a classic synchronization problem in which we have many threads that want to access shared sources. In this case, we are talking about forks. So we have this scenario. We have, in this case, 5 philosophers, 5 forks, and a bowl of spaghetti. Every philosopher wants to eat spaghetti, and to do that needs 2 forks, right? So you immediately see the problem. We have collisions, so we cannot have all the philosophers eating simultaneously. So we have to orchestrate this accessing to the actual forks. So for the data structure part, what is a philosopher? Well, a philosopher indeed is a struct that contains some data. For example, we're going to have an ID, right? In this case, we have ID equal 5. It is the identifier of the actual philosopher. Then a pointer to a left fork, a pointer to a right fork, and the number of meals consumed, and other variables, right? We will see while we are coding. So a philosopher is just a struct. We are gonna create 2 arrays of structs. So this is the way by which I model the problem in such a way that the computer can solve it. But what is a fork? Well, a fork is a mutex, of course. So we're gonna have an array of mutexes. An array of mutexes. Long story short, we're gonna have an array of philosophers which are these structs containing member variables, data, and an array of mutexes that are going to act like forks in our problem. So this is it. The problem is modeled in this fashion. Two arrays. Let's now create the actual philosopher struct. So it's going to be Philo, and let's say struct as Philo, and let's start from the member variables. We're going to have an ID, as we saw, ID. Then some variables, internal variables. So let's start from meals counter. This is going to be indeed a counter of how many meals the philosopher has eaten. A boolean to say if the philosopher is full, because we can get an input like that. Philo 5, 800, 200, 200, and this last is conditional. It's not mandatory, which is the maximum number of meals that the actual philosopher can do. So we're going to stock all the meals done by the philosopher inside this variable, and here we have a flag that is going to be turned on if the philosopher has eaten the maximum number of meals, okay? So we're going to see this while coding, but just to show you that these member variables are very useful to solve this problem. Then we're going to have a last meal time, other very important member variable, because this is going to keep track of time passed from last meal. And this is very important to check if the philosopher has died, because we're going to have time to die, which is the first parameter. If the time elapsed between meals is major than time to die, the philosopher is dead. So this is another important variable. It's going to be a long because we're going to use microseconds in our project. And of course, a pointer to the actual forks, which are mutexes. Now let's do something. I want to create a struct for a fork. You will see immediately why. So struct fork. A fork is going to be a mutex. Now I don't want to use this long data type, pthread mutex type, right? So I'm going to use a typedef here at the top. Typedef pthread mutex type, and we call it type mutex, like that, very short. This will make the code more readable. And the fork is going to be mutex, of course, so type mutex, and also is going to be an ID, which is going to be fork ID. This is pretty useful for debugging, this ID, because I know exactly which fork the philosopher has taken. So let's do immediately a typedef here, type fork. Of course, all the times I don't want to write this, so the typedef is pretty handy. All right, let's go back in our philosopher. And here, what do we have? We have a pointer to the left fork and a pointer to the right fork, okay? Then, of course, crucially, we are going to have a pthread type, right? Pthread type, which is the thread ID, namely a Philo is a thread. We're going to feed this value to pthread create, okay? So by now, this is it. By now, this is our philosopher. Of course, we're going to use also here typedef. So typedef Philo. And by now, we are done. We have a Philo, we have a fork. We now need a container. We need a struct in which we can stock all the data, like the number of philosophers, the time to die, time to sleep, time to eat. So we're going to create another struct that I call table. Basically, this is a container of all the data. And let's do that. Typedef struct table, type table. Perfect. And inside our table, a good name also would have been here, data, general data, global data. You do that. Table just because it recalls like all the simulation. Here we're going to put all the inputs received at the command line. So we're going to have long Philo number. This is the amount of philosophers, namely this value. Long time to die, which is this first parameter. And the pattern is simple. Time to eat, time to sleep. Okay. Then a long number limit meals. This is going to be the 5 in this case, right? And this variable is going to act like a limit or like a flag. For example, if it is -1, this is going to be a flag in the sense that at the level of the command line, we don't have this input. Okay, so this is a bivalent variable, both a flag and a value. Then we're going to have another long, which is start simulation. This is basically the time when the simulation is starting. This is important because I need timestamps from the start of the simulation. Basically, all the philosophers will have timestamps starting from this value. Then I will have a very important bool, which is end simulation, which is triggered when a philo dies or all philos are full. So this flag is turned on in these two scenarios. Then there's going to be, of course, other data, but by now let's do only forks. Basically, this is the array to all the forks, and type philo, an array to all the philosophers. Now here I want every philosopher has access to these global quote-unquote values. So I need a type table pointer, but here I will get a mistake probably. The compiler yells at me that it doesn't know this type table. So we're gonna do that. We're gonna for front declare this at the very top and set typedef struct type table. Like that. Basically this is an IOU for compiler. I'm telling this table exists, don't worry. So I can use inside my philosopher. So you see, it is kind of recursive. I have a table that contains the philosophers have a pointer to the actual table. This will be super handy because when I pass a philosopher, basically I have access to all this data. So I think we have enough stuff to start our simulation. So let's create a main.c. Let's start from the main. So immediately we include our philo.h and basically we are ready to start. The main is a TLDR of the program. Indeed, from main, we should be able to understand the overall project, the overall application. So int main, int argument counter, char star argument vector, and we're going to start. Keeping with the fact that the main is a TLDR of the application, I would say that we're going to check if the input given at the command line is correct. We're going to kick in the machinery. Otherwise, we're going to prompt the user to please feed me with a correct prompt. How do we do that? Well, the input is something like that, right? Philosophers, time to die, time to eat, time to sleep, and potentially number of meals. So we can have 1, 2, 3, 4, 5, or 6 inputs, right? So I'm going to say if 5 is equal to argument counter, or 6 is equal to argument counter, here we have a correct input. Correct, quote unquote, namely we have the correct number of inputs, right? Then we still have to parse and to check if effectively the input is correct, but nonetheless, this is the first filter. On the contrary, we are sure that the input is wrong, so we have to prompt the user the input is wrong. Okay, we're gonna print an error, and here I'm gonna immediately create an utils. I want a function that is printing an error and is going to exit, because I will call this function many times throughout the code. So let's create our utils.c. So as usual, I include philo.h, our header, and I want a stupid error function that is prints an error and it's going to exit. So void error exit, that is taking a string literal, so const char star error, and is going to printf the error, so %s new line, and I want to after that exit with exit failure. Now I want to customize a little bit this. To do that, we are gonna in philo.h put some ASCII escape sequence. To do that, I'm just gonna ask ChatGPT to write me some ASCII escape sequences for the printf. So this is the result from ChatGPT for doing these repetitive things. Is amazing. So I get red, green, yellow, blue, magenta, cyan, white, and there is that. Everything is bold. Perfect. Pretty fast. So I can use this in my printf to make it more cool. I feel cool there. So let's go to utils, and I'm gonna make my printf red, and then every time I have to reset. This is just the way it works. Reset. All the times I copy and I paste in my header file, because we need all the prototypes here at the bottom. All right, utils. So we go back to the main, and here we simply call error exit with wrong input. And then maybe we can say new line. We can go in a new line. We say green here, and reset to make it the correct is we pass this one. Boom, we are okay like that. Now for the actual meat of the main function. First of all, we have to declare a table, of course, a table that will contain everything. And if the input turns out to be correct, at least number-wise. First of all, what do we do? First of all, we're going to parse the input, giving as an input a pointer to the table, because we have to put inside the table all these values, right? And of course, argument vector. This is going to be a function controlling errors checking, filling table data, like that. Second is going to be data init, still pointer to the actual table. This is going to be initting all the actual philosophers, mallocing philosophers, mallocing the forks, and so forth. So creating the actual thing. And third point is going to be the actual simulation, I guess. I can call it dinner start. Still, I pass the table by reference. You see how cozy it is to have just one struct. And if I pass this, I have access to everything. And then probably is going to be the last function, a clean function. Clean at table, no leaks. Okay, so this is the roadmap. First of all, we parse the input, then we need the data, we start the simulation, and then we clean when the simulation is finished. Either when Philo is full, basically all the Philos are full, or one Philo died. This is when we're going to reach this clean function. Otherwise, the loop is going to be endless. All right, we're going to start by parsing the input. So we're going to create a model, a file. That I call parsing.c. As always, we are going to include philo.h, and we're ready to go. So we start from the function void parse input that takes as an input the actual table, a pointer to that, of course, and argv. Boom, let's start. So we understand that we have this input, right? Basically, what I want to do is to take all these parameters, which are AV in position 1, AV in position 2, AV in position 3, and so forth, right? I want to take these strings and convert it to actual integers, to actual values. Doing that, I want to control if the strings are actual numbers, right? Actual numbers. And two, not major than int max. Then we have also to do the controls if timestamps major than 60 milliseconds. So we're gonna do all of these controls. To do that, we're gonna need a function alpha to not to integer but to long, because I want to control also the int max. So we're gonna create an alpha to long function beforehand, because we start from here, right? I'm going to need to say table Philo number is equal to alpha to long, right? So we have to create this alpha to long. We're going to do immediately. So a long, 50 alpha to long. As an input, we have a string, const char star str, like that. Now, given that this is a function that I'm going to use only inside this module, I say static, okay? It means that this function is useful only here in the parsing module. It's not going to be used in other modules. So of course I'm going to declare a long number. Inside this variable is going to be stuck the actual number that we're going to return. And of course we have to initialize to 0. This is easy to forget, and it's fairly common to me to spend hours to find these stupid bugs because I don't initialize variables. Always initialize. I can do a trick here. I can say str is equal to valid input. I pass as an input str. Now I will explain you what I mean. So let's create immediately valid input. This function again is a static. It's going to return me a const char star valid input and takes as an input a const char star str. So what is the goal of this function? What I'm trying to do? Check for negatives. If there are negative numbers, this doesn't make any sense, so the input is wrong. Then check if the number is legit, right? Legit, I mean I can have spaces, I can have a plus, I can have a 77, and then I can have after that some other symbols like that. This is a legit number. We are gonna indeed skip all the spaces, and then we take the 77. This, on the contrary, is not a legit number, because it is not. All right. 3, I do a check for int max initially. Check for int max. What do I mean here? Given that this is a string, I mean that if someone inputs a string like that, which is a number, but it is not a legit one, it is way too big. I cannot even stock inside the long because it's way too big. So the skill is that I will check for len initially. Check for len. Namely, int max is 2 billion for 47, I think, or 48. No, 47, I guess, for int max. But not the problem, not an issue here. What I want to tell you is that here I have 10 chars, right? 3, 6, 9, 10. So I say if len major than 10, I'm already sure major than int max, right? This is not a complete control because I still have to check for the values ranging from this to 999, 999, 999, right? I still have this set of numbers to check. But anyway, this is a first filter, string-wise, still to check. I will do a check in this in my alpha to long function, okay? So why this function returns a pointer? Well, the function is going to return a pointer to the actual number. For example, if I have this number here, the function is going to return a pointer to the 7, you see? So the function alpha to long is going to start processing immediately from the digit, all right? We have already cleaned our string, all right? Hopefully what I said makes sense. And now we're going to see the code. So we're going to need an int len. In this, we're going to accumulate the len of the string, and const char star return, or we say better number. So this is a pointer to the actual number that is going to be processed. All right, len of course equal to 0 all the times, don't forget. And first thing, skip the spaces. So I say while is space. So I'm going to create an ad hoc function here at the top. Again, I'm going to do static bool is space char c, staking a char, and very simply it's gonna return a boolean, and I say c is major equal than 9 and c is minor equal than 13, or c is equal to 32. You understand, right, what I'm doing here? Just watch the ASCII manual, you will see all the charts, and basically I'm saying from 9 to 13, which is horizontal tab, new line, vertical tab, carriage return, or 32, which is the space. Basically what I'm doing is recreating the function is space, you see, all this character. As simple as that. Now here we can also do something more. We can say static inline. Basically we're saying to the compiler, hey, just boost the performance of this. Treat is not like a normal function, but simply quote unquote copy paste this here, right? Because the thing is that I can simply write this inside the while loop, right? But I would argue it's not as readable as writing is space, because here if I do while is space at str, you see how readable it is. If I write directly, this is super quick in my opinion. So that's why line functions are useful, because are more readable. That's it. So what do you want to do until you have a space? Well, you want to skip, so you're going to increase str. So you do pointer arithmetic plus str. All right, now you don't have any spaces, so you say if at str is equal to plus, okay, it can be, so you go on, pointer arithmetic. Else if at str is equal to minus, this is wrong. So we're going to call our beautiful function error exit with feed me only positive numbers, positive values, you say. Okay, so at this point we can have the symbols. Then I say if not, and here I have to check if the actual char is a digit. So we're gonna do the same trick as the ispace. I'm gonna create a little inline function at the very top. So let's do that. Static inline bool is digit char c, like that. And on the same line we're gonna do c major equal, we're gonna use the chars here, 0. Here we can also use 48, but it's more readable. And c minor equal 9, like that, right? Super simple. So here I say if not is digit at str, error exit, the input is not a correct digit. Okay, on the contrary, it means that we have stumbled upon a digit, right? So we can say number, our pointer, right, is equal to str. This is the return string, right? It's the return pointer to the actual number. Okay, so alpha to long is going to receive a pointer to this 7 here, right? Because we have skipped all of this. Then the final check do for the actual len. So I simply say while is digit at str plus plus len. And of course I have also to increase here the pointer. So while at str plus plus, you see? Okay. Final control, I say if len major than 10, error exit, the value is to int max is the limit. Then at the very bottom, we're gonna return number. Okay. I think it's fairly simple, this valid input, right? What do you think? Okay, we keep going on with our alpha to long. And as you can see, a lot of work has been done by my valid input. That has returned me a pointer to the actual string. Now we simply have to harvest the actual integer value. So here I say while is digit at str. What do you do? Number is equal to number per 10. Of course, we are in a base 10. Plus what? Plus the char pointed by str minus 0. Char 0, right? Because this is minus 48 if you want. Maybe here is clearer. For example, here if I have the char 1, which is 49, in the ASCII table, right? The char 1 is 49. I will get 49 minus 48, which is actually 1. 1, that's the integer value that I'm looking for. Here, of course, I also have to increase str all the time. So the first time I will multiply 0 per 10, 0 plus 1, for example. The next iteration I will have 1 per 10 is going to go on the next order of magnitude, and we keep going on. This is the algorithm to harvest a value from a string. Then we have to do the second control of int max. So if number is major than int max, again, error exit. And we copy the string here, like that. Finally, we simply return the number, converted to a string, converted to an actual long, right? So that's basically it for me, for my alpha to long. The big work has been done by valid input. You can see these are all static functions solely used inside this model. And now we keep going on with the actual parse input function, the one we care the most. So now we're gonna take table time to die is equal to the same pattern, right? Time to die, argument vector in position 2. Now the timestamps here are given in milliseconds, right? 100 milliseconds, milliseconds. The thing is that the useLeap function wants microsecond. So I think that I can do here immediately to ease my life is to convert immediately these values in microseconds. How do I do that? Well, microseconds are like kilo, mega, giga, right? We have kilo, mega, giga. And in the same vibe, we have milliseconds, microseconds, nanoseconds. So it is 3 orders of magnitude smaller. A microsecond is 3 orders of magnitude smaller than a millisecond. So here, I think that the scientific notation is pretty handy to do the conversion, because here I would do like that, per 1000 to do the conversion. But I can do per 1e3. Basically, 1e3 is 1 with 3 zeros. It's super easy, right, to make conversions in order of magnitudes, thanks to the scientific notation, right? Now we're going to use that. I do the same also for the other values, time to die, time to eat, and time to sleep. So argument vector in position 3, argument vector in position 4, all already converted. Then I have to make a check for 60 milliseconds. So I do if table time to die is minor than what? 60 milliseconds. You can write 60 and then convert to microseconds with 3 zeros, or you can do 6e4. Like that. Then the pattern is self-similar, right? Time to die, time to eat, or table, time to sleep, minor 6e4. What do? You error exit, use times major, and then 60 ms. All right. Now, the last thing we are going to do is to check if argument vector in position 5 is present. In this case, we're going to say that table number limit mils is equal to ft alpha to long av in position 5, right? Else, we're going to use this variable as a flag, giving -1, like that. Boom, we have the controls. Maybe there is some bug somewhere, I don't know, but By now it seems correct. And we're gonna run and we're gonna check for potential mistakes. The only thing we have to take this function, only this function, because the other ones are static, and put inside philo.h in this fashion. So we do parsing and we pass it. Perfect. Go back to the main and the parse thing is done. We can remove that to do. Now we pass to data init. We have to actually create stuff. So let's create another model that I call init.c. We of course include the header philo.h, and we start our journey. We do void data init, and as an input we take a pointer to the actual table, right? And now what we want to do, let's go back to philo.h. Given the table, we have all these values that's already set, right? Start simulation we're going to do later, the boolean and simulation. We're going to settle these three. We're going to malloc first, the philosophers, and simulation we're going to put false. So table and simulation is equal to false. This is a very important boolean we're going to use a lot. Then we have table philosophers is equal to what? Is equal to malloc the number of philosophers. Now, every time we call a function like malloc, we have always to check the return value if null. Never happened that a malloc return me null, you tell me, but we have to do that. So I create a model, a doc, that I call vim save functions. You will see what I mean. I'm gonna include philo.h model containing wrapper functions with embedded controls on return. What do I mean by that? The goal is to create a very short main code, so I don't want to control the error returning from the function, both from the malloc but also for the pthread functions, which are all self-similar. We're going to start from the malloc so you can understand what I actually want to do. So void star save malloc size t bytes, right? So I'm going to do void star because the malloc is going to return a generic pointer, a void pointer, and then I'm going to simply do return is equal to malloc bytes. Okay, and then I do the control here. If null is equal to ret, exit error with the malloc, like that. On the contrary, return ret. As easy as that. So you see this save malloc is just a wrapper with an embedded control. So when I will malloc my philosophers, I will show you. At this point, I will simply call save malloc. Okay, see how cleaner becomes the code. I do save malloc table number of philosophers, so philo number. Boom, easy as that. Now let's finish our save functions. I want to use many more of them for the pthread API. I will show you immediately. First of all, let's start from mutexes. Mutex save. So there are basically 4 functions that I can use for mutexes, which are init, destroy, lock, and unlock. Okay. The idea that I have is just to have one simple wrapper function like that, void save mutex handle, that is taking a pointer to the actual mutex, so type mutex, and is going to take an operation code. An operation code that is going to be an enum. Now I'm going to show you. So let's go back to my philo.h. And at the very top, we're going to create an enum for mutexes. Opcode for mutex and threads function. Let's do that. So enum opcode. And inside, we're going to put everything I can do with a mutex or a thread. So lock, unlock, init, destroy, create, join, detach. So you see, I'm going to create a lot of symbolic constants. Every symbolic constant is going to have a value. I think it's going to start from 1 or 0. I don't actually record, but it's not important here. Here I'm going to use a typedef, again, type opcode. So now I'm going to show you how I use this stuff. Let's go back to my save functions. And here my save mutex handle is going to take an opcode, which is going to be an enum. And here we simply say, if lock is equal to opcode, you call the specific function, which is, in our case, pthread mutex lock, with a pointer to the actual mutex, like that, right? The pattern is self-similar, right? So else if unlock is equal to opcode, you call the actual function pthread mutex unlock. Else if init is equal to opcode, you call pthread mutex init. We pass the mutex, and the second parameter is attributes, but we don't really need those, so it's going to be a null. Else if destroy is equal to opcode, you call pthread mutex destroy, okay, with the mutex. Else you simply say error exit wrong opcode for mutex handle. Now you may say, okay, what's the gist of it? Why it can be cool to have the save functions? Well, because now I'm going to create an embed control on returns to make this more valuable. So embed controls on return value status. So it's going to be static void. I'm going to call handle mutex error. And as an input, I receive a status and an opcode. So type opcode, opcode. What is the gist of this function? We're going to check the return value. So if 0 is equal to status, you simply return everything is correct. Now we're going to understand why. So here you can see all the action functions: unlock, lock, init, and destroy. As you can see, they are all self-similar. All these functions will return 0 if they are correct, otherwise we are going to get an error value, which is this one. As you can see, all the functions return an inval. The value is not correct. The string is, for all of them, similar. So the thing that we have to do is to handle these return status values and print the correct string error. We're going to basically recreate the p error function that we cannot use in this project, and that is not working because these functions, as I understand, are not going to set the no global variable. So the only thing is to do manually. I say if inval here to use this symbolic constant, I have first of all to include it to my fil.h the no error file. So include no. So let's go with the logic. So I say if inval is equal to status and lock is equal to opcode, or unlock is equal to opcode, you call error exit and you pass this string here. The value specified by mutex is invalid. Okay, else if inval is equal to status and init is equal to opcode, error exit, we got this string this time. Cool. Else if this time we take this deadlock is equal to status error exit. This is kind of tedious, but it will be super useful. We copy the string here. Else if perm is equal to status, the current thread does not hold the lock on mutex. Else if omen, this is the classic mistake, not enough memory, error exit. Else if busy is equal to status, error exit, mutex is locked. All right, so now what's the gist of it? Well, the thing is that I will wrap around my functions here into my handle mutex error. See, the function, the opcode. So I will do this for all the functions. Boom, here it comes. This is the final result. It has been kind of tedious to create, but now when I want to use a function coming from the pthread API, for example, mutex lock, mutex unlock, init, or destroy, I will simply call that. I don't care anymore about potential errors. This is gonna all be taken care of by this save mutex handle. I will do the same for the threads. It is exactly the same pattern, so I will just code it and I will show you the final results. So this is gonna be the same thing for threads. I have my save thread handle. Of course, the prototype of the function is a little different because I have my pthread create function that requires more details. For example, I have a pointer to function, as you can see here, right? The strange pointer function signature, then data, but the idea is exactly the same. I have a wrapper function, which is this save thread handle that is going to take a pointer to the thread data type, a pointer to function, a pointer to data, a pointer to opcode, and I can call create, detach, and join. And then all the controls are embedded in the save thread handle. Not complicated to understand. So I'm gonna copy all of these prototypes in my header file here and save mutex handle like that. So now I can use this function. I can basically forget about this model, and we raised the level of abstraction of my code. So in a very compact way, I can use malloc and all the functions from the pthread API. I think this will make overall the code much more clear. All right, now let's go back to the actual init. And we made a lot of functions, save functions. So table philos is okay. Then we do table forks, same, save malloc, table philo number, but here I just forgot to put the size of operator, stupid mistake. Here I need size of type philo per philo number, and here I need size of type fork per philo number. Cool. Then I need to init all the actual mutexes, all the actual forks. So I'm gonna have an iterator, the legendary I iterator, which is -1. I like to start by -1 to do this, while ++I is minor than table philo number. We're gonna finally call my save mutex handle function, and we pass as an input table forks in position I need to take the fork. I have to pass by reference like that. The opcode is gonna be init, right? Because we want to init this mutex every time a mutex has to be init. Init. That's it. You see how clean it is. And then we say table forks position I dot fork ID is equal to I. So every fork is gonna get a specific number. This is gonna prove super useful for debugging. Nice. Then we have to init the actual philosopher. So I'm going to create a function that I call philo init, and as an input I give the table. All right. This again is going to be another function static philo init static void philo init type table like that. So basically here for every philosopher we have to give an ID, mills counter, full, and init all this data, and of course assign the forks. So let's do int I is equal to -1, and I say while ++I minor than table philo number. Here to make the code cleaner we can say type philo, a pointer to philo, and philo every time in the loop is equal to table philos plus I, right? This is just pointer arithmetic. Then I simply say philo ID is equal to I +1. Then philo full is equal to false, of course. Then philo last mill time, we don't care by now, mills counter is equal to 0. Then we have philo table is equal to table, very easy. And philo, we have left fork and right fork, which is important. Right ID, we don't care. So now we need to assign the actual forks, and this is a very important step. So I'm going to create an doc function that I call assign forks. Philo and table forks, and also I. I is basically the position in the table. Now let's do that. Static void assign forks, that takes as an input a pointer to philosopher, then a pointer to the actual forks, and an int position, relative position in the table. And now we have to understand a very important concept about fork assignment. So we have our philosophers, right? We have this array of structs and our mutexes as well, which are the forks. When it comes to fork assignment, what do I want to do? First of all, we have to really be aware that philo ID is not the relative position in the array, right? Because we start by 0, but the first philosopher has ID 1. This is important to keep in mind. Let's see the actual visualization of the assignment, so it's gonna be easy. For the right fork is pretty straightforward, right? We have the position, which is actually the position as well of the fork. So we can simply assign the right fork thanks to the position value. For the left fork, the thing is more tricky because we are in a table, which is a modular object, essentially like a clock, right? A circular object. So what do? We're going to focus our attention to philosopher number 5 because we can understand the principle here. So we zoom in and we see that the left fork of philosopher number 5 is the 0. So what is the operation? Well, it's pretty straightforward, right? Left fork is equal to the position of the philosopher plus 1, because it's the left fork, modulo the number of the philosophers. So we're going to have 4 plus 1 equals 5, modulo 5, 0. You see? The reminder. That's as silly as that. We have just to keep in mind that the table is a circular object, so we have to use the modular operator. So we do this for all the philosophers, and we see that we get this, that every philosopher has a left and a right fork. Indeed, that's what we need to do our simulation, given that every philosopher requires 2 forks to each. So let's do this in code. So here immediately you can understand why I used a position here, which is actually the I value of Philo init, right? Because it's cleaner than every time writing Philo ID -1, right? Or to write a new variable. So we said that we need the actual number of philosophers. So I'm going to create an internal variable to make the code cleaner that I call Philo number. And Philo number is going to be equal to Philo table Philo number. It's just a way to make the code cleaner. And then we simply do the operation that is Philo right fork is equal to the position, right? Equal to position. So very simple, it's going to be forks position, right? Or better, here to make it cleaner, I can do Philo position. Philo position. So right fork is equal to forks in Philo position. And that's it. Given that we have to give back a pointer, we're going to use the ampersand. As easy as that. On the contrary, Philo left fork is going to be different. It's going to be forks in position, Philo position +1, right? In parentheses, modulo Philo number. Modulo Philo number, like that. And then we use the ampersand. All right, this is the fork assignment, which is not difficult, right? But here the problem is a potential deadlock here. Now I will show you why. Basically, a deadlock happens when we have multiple threads that are stuck because they're waiting for a resource to be freed from another thread. Namely, we have a circular waiting. Thread 1 is waiting for thread 2 for thread 3, for thread 3 from thread 1. So we have the circular waiting. Now I'm going to show you. Let's pretend that every philosopher is going to take the first fork left. What is going to happen? Boom. We get that every philosopher takes the fork and is waiting for the right one, but it will never free. This is a circular waiting. This is a deadlock. This can work. This fork assignment can work if we desynchronize the actual fork taking. We can say that if philosopher is odd, it's going to wait for X amount of time before actually trying to take the fork. So it can work, but we are in a random arena. We don't want that. We want the code to be more robust. We want the code to be 100% deadlock free. So this fork assignment is not going to be good. Furthermore, if you compile with thread sanitize, you will get this deadlock problem, even though your code can actually work. So what is the solution to this deadlock issue? Well, I found online that there are basically 2 solutions. One is the Dijkstra solution, in which only one philosopher is taking the fork in reverse. The last one is taking the last fork in reverse. Or the odd even solution, which is the one I use in my code, in which basically we have that if you are an odd philosopher, you're going to take the first fork, which is going to be the left. On the contrary, if you're even, you're going to take the right fork first. How does it work? Well, it's fairly simple, right? We have all the philosophers that are going to have a first fork target, and this will create some contention areas, as you can see. We have philosopher 1 that has contention with philosopher 2, the same for 4 and 3. In this case, when we have odd philosophers, we have the 5 that is kind of the difference dude in the table. But this will work. Why? Well, let's try a simulation. We have that in our first case, philosopher number 2 is going to win the contention with number 1, and philosopher number 4 wins the contention with number 3. So 1 and 3 are forced to wait, right? Because they are waiting for mutex that is locked. Boom, they stop forcefully. Number 5, in our case, is idle, but he could have taken the fork number 0. Then we get that number 2 and number 4 took the second fork, and they can eat. They can eat now. Then they will release the actual fork. They will unlock the forks. And now we start again. We have, again, competition, we have contention, and every philosopher is going to try to take the forks. But you see that in this way, we have constraints. We cannot have all the philosophers reach the fork and create a deadlock scenario. Let's just watch the possible worst case scenario. What is going to happen? The worst case scenario can be this one. As you can see, we have only one philosopher with 2 forks, and 4 philosophers are waiting. But let's have a quick replay of what is going on to understand better. We have our contention area, and the first philosopher is going to win the contention with number 2. Then we have that number 5 takes his own fork, right? It doesn't have contention for that fork initially. So we have number 5 and number 1, they are reaching the fork immediately. At the same time, we have number 4 that wins competition with number 3, and at the same time wins competition with number 5. So that's the scenario. You see, in the worst possible case scenario, you don't have a deadlock. At least one philosopher is eating. So this even out assignment is robust. It works, is deadlock free. Now the problem is fairness, but we will see how to solve this issue as well. So this is what I'm going to do. This will prove deadlock free. Okay, that's the main idea. Hopefully this is clear. So one thing that I want to immediately do is to go back to my philo.h and change the naming. I don't want left fork, right fork. I just want first fork and second fork, because we're going to do the odd even assignment, and this is cleaner. Then back to init, and we say this is going to be true if the philosopher is odd, right? So if philo id model true, you're going to have this fork assignment. Namely, first of all, you take the right, and then you take the left, which is going to be first fork, second fork. On the contrary, we just copy this, is exactly the reverse. So very easily, we're going to change it to second and first, like that. All right, so we managed to assign the forks, even not fork assignment. All right, I guess we have almost finished this init file. Then while we are coding, we can add some other variables, of course, but by now it's fine. We have our philosophers, we have malloced the forks as well. We have init all the forks, and every philosopher has a fork assigned. So basically we are here. We have the model of the problem on the table, right? Is ready to be run. Okay, we simply copy data init in our header file. Boom, and we go back to the main. Init is done. Now it's time to actually start the dinner start. So we're going to create another model that I call dinner.c. All right, we include Philo, and here is going to be the actual meat. It's going to be the actual simulation of the dinner. Before starting the simulation, let's refresh the input. The input can be something like that, right? So I'm gonna do if no meals, just return. Namely, if here I have 0, just return. You go back to the main, we call the clean function, done. Then we have to take care of if only one philosopher, one philo, you do an ad hoc function. Then we go back to the main thing, which is create all threads, namely all philosophers, which are going to run a specific function. Create a monitor thread. This is going to be a thread that is searching for philosophers which are death. We have to synchronize the beginning of the simulation, because every time you call pthread create, the philosopher start to run. I don't want that. I want every philo start simultaneo. So we need a synchronization thing to make all the philosophers start at the same time. And then we simply join everyone. All right, let's try to code and understand everything. So we do void dinner start, and as an input we have a pointer to the table, right? Type table. So immediately I say if 0 is equal to table number limit meals, you simply return. Go back to the main, we are finished. Back to main clean. Else if 1 is equal to table number philo number, we're gonna do it later to do a doc function to handle one philosopher. Else we have to create all the philosophers, so we're gonna call our wrapper function safe thread handle. We have to pass the address of the thread ID, so we do that. We need an iterator. I is equal to -1, and you say while plus I minor than table philo number. you create all the threads. So it's gonna be table philosophers in position I. We're gonna access thread ID and we pass by reference. Okay, so this is a pointer to the thread ID of the I philosopher. Then we have to pass a pointer to function, which is gonna be dinner simulation. Here I don't need an ampersand, this is redundant. Already when the compiler sees a name of a function without the parentheses, already understands that this is just a pointer to function. We're gonna pass as a data the actual philosopher itself, so Philo is in position I by reference. And the opcode is gonna be create. Okay, that's it. This is a while loop that is gonna create all the threads, all the philosophers. And I repeat to you, every time this function is called, immediately the thread starts running this dinner simulation function that we still have to do. So we need a synchronization thing to make all the philosophers start at the same time. All right, I would create my dinner simulation function. So the prototype is clear, void star, a generic pointer, dinner simulation, and as an input I get another generic pointer I call data. So we have to fetch back our philosopher. So I'm gonna create a variable type Philo, pointer Philo, and this pointer is equal to, I type cast back to a pointer to philosopher, the actual data, like that. So in this way we manage to fetch back our data. Of course we put a return null here. So we set here that we need await all philos, synchro start. So before end I need this synchronization thing, and then the actual endless loop, right? The actual endless loop, and now we'll see endless loop of the Phil. So to wait everyone, we're going to do a function that I call wait all threads. Let's put to do. Now we go back into Philo.h and we put in our table another boolean which is all threads ready to synchro philosophers. As well, we go back to init all the time. We go back here and we put another false here, all threads ready equal false. Okay, we go back to dinner, and what is the thing I'm trying to do? This function is going to take the table as an input because it contains that variable all threads ready, and now we have to understand how to engineer the thing if you want. The thing that we're gonna do is that at dinner start, after this while loop, we're gonna say, hey, now all threads are been made, right? Already, right? Just after the loop. So we can set that boolean all threads ready to true. The thing is that we are in a multi-threaded environment, so accessing a shared variable is gonna be a race condition. So we need to protect this boolean with a mutex. We're gonna go back in our Philo.h, and in our table we're gonna create a mutex. We're gonna create a mutex, type mutex that I call table mutex. Avoid races while reading from table. Of course, we go back in our init all the time. We have to do that when we create something new, and we just init this mutex. So we do save mutex handle table mutex init. Easy, right? With my save function, the control are already made, so I don't need to worry about anything. Okay, now we have this mutex in the table. Let's go back to the dinner, and here the idea is that I will lock that mutex, set the boolean to true, and then unlock 3 lines of code. This is not cool. This is not cool. I don't want to write all this lock unlock everywhere in my project. So it's time to create getters and setters to make the code much more cleaner. We're going to create a model getters and setters. So include Philo.h. So model to avoid writing lock unlock everywhere. Okay. So in the main code, I will have set value to that. I don't know about locking, unlocking. This will happen underneath. It will happen thanks to these functions that now we will create. So we start. The thing now that you can clearly see is that there is a reason why I've chosen only long and bools, because I want to use only two types of getters and setters for booleans and for longs. And I'm settled for whatever data type in my simulation, right? So we started by booleans. The first is going to be set bool. That is going to take a mutex, right? That's the gist of it, a pointer to a mutex. And it's going to take a pointer to a boolean, I call dest, and an actual value, okay? Then the pattern is pretty straightforward. You are going to lock, unlock, and set the value. So you're going to mutex lock, copy, paste, unlock, and in the middle, you just have at dest. We're going to reference the pointer is equal to value. Boom, that's it. You see? Now we're going to do the function get bool. So get boolean, same pattern, type mutex, and a pointer to the actual boolean that I want, that I call value, like that. So we create a return value, bool ret, we copy here, lock, unlock, and here we actually have the reading thing, the reading of the value thread safe. So we say ret is equal to at value, and then we simply return ret. So you see the pattern is pretty simple. We do the same for longs. So as you can see, the pattern is specular. We just simply change the data type, and that's it. We have some thread safe functions to get or set some values. At the bottom, I want another one which arguably is redundant, but in my opinion, it's useful, which is bool simulation finished. And let's say we pass the table that contains all the variables, and we simply return here get bool table our mutex, so table mutex, a pointer to the boolean, which is table, and simulation, so a pointer to that. Here comes this simulation finished is just a wrapper for a get bool that we just created, but I think that calling this function is useful. All the time you see very clearly simulation finished is simulation, because we are gonna use this simulation finished a lot of times throughout the code. So for me, the code being readable is part of being correct. If the code is not readable yet it functions, to me it's not totally correct. I mean, because it's not maintainable, it's difficult for myself to understand what I did. So readability is very, very crucial to me. Otherwise I will spend hours in debugging without understanding what I'm doing. All right, so the thing is that we have to put all this function in our header file. So we go back in our header and we simply copy all the prototypes so we can use throughout our code. I think these functions are super handy, right? Without writing all the time, lock, unlock. Let's go back to our dinner, and now we can start using. After our while loop, we do set bool. We pass the table mutex by reference. The destination is going to be table all threads ready, right? Still by reference. And the value is going to be true, like that. So after our while loop, now we set this. Now we go back to our dinner function, dinner simulation, wait all threads. Let's create this. We're going to create another model that I call synchro utils. Some function to synchronize. We're going to need others also for the monitor thread. So this file is going to prove useful. Include philo.h. So what is the idea here in our dinner? We have wait all threads. This can be a spin lock, namely we are making the actual thread run, spin locking, a while loop, a busy waiting, call it as you want, until all the threads, namely the flag, is set to true, this flag here. So we're gonna do that. We go back in synchro and we say void wait all threads. And as an input we have the table, so type table, pointer to that, and we do a spin lock. So while we use our save function, so get bool table mutex 1%. The value is table all threads ready, right? Reference. And here importantly not. So while all the threads are not ready, you just wait. So you spin lock. That's it. So spin lock to synchronize Philos start. Okay, we just copy the prototype and we passed in our header. This is tedious, but in C we have to do that. Synchro utils. Boom, done. Wait all threads. We go back. And now we have our synchronization thing. Every philosopher is going to actually wait for all the threads to be ready before going on. All right, cool. We can remove that to do. So now let's go back to our dinner And we can say at this point, well, now we are into business. The simulation has started. Start of simulation. Or better, start of simulation we put just before here. So here we have to basically take the time of our start of simulation. So we need a chronometer. We need a function that is able to give us back the actual time. So we're going to create this function. We go back to our utils, in which we already have our error exit function. And we're going to create our chronometer function thanks to get time of day. We're going to exploit get time of day. So if we watch the manual, we get that thanks to get time of day, we get the time since midnight, January 1st, 1970. We have to use a struct, which is time val. And inside this struct, we have the seconds since January 1, 1970, and the usec, which are the microseconds. So we can exploit this get time of day to get whatever time we want, seconds, milliseconds, microseconds. Now we're going to do that. So we are going to go get back time, which is a long. I call the function get time, and as an input, I want to use a specific time code in the same vibe of the previous opcode for mutexes and threads. So we're going to create an enum. The time code is going to be seconds, milliseconds, and microseconds. Probably seconds are not necessary, but who cares? It's very simple. So let's go back in our philo.h and let's create these enum codes for get time. So enum time code. We're going to have second, millisecond, and microsecond. Okay, of course we're gonna typedef everything, type time code, typedef. All right, so these are gonna be all symbolic constants to our get time function. Let's go back to utils. So our get time is gonna take as an input type time code, which is time code. All right, immediately we're gonna create struct time val that I call TV, and we call the function get time of day. Get time of day as an input, we get a pointer to our time value, so pointer TV, and the second parameter we don't really need, so it's going to be a null. So basically get time of day is going to set the seconds and the microseconds inside my time value. Now the return value of get time 0 return value indicates they call succeed, -1, and set error no if something. So we're gonna make a silly control here. So I say if I have some return value, you're gonna exit error, even though it's highly improbable. Get time of day failed, like that. All right, now I have my seconds and microseconds inside my time ball. What can I do with that? Well, I simply check the time code. If second is equal to time code, what do? Do you want to return the actual seconds? So you're gonna return time value, I access seconds normally, plus time value microseconds, and here we have to convert in seconds. So we're gonna use scientific notation, which is divided 1e6, right? To make the conversion. Then the pattern is the same, right? Else if milliseconds is equal to time code, we're gonna return time value dot second. This time we have to convert this in millisecond, which is gonna be multiplied by 1e3 plus time value microsecond. This time divided 1e3. All right, the last one, else if microsecond is equal to time code, you just return time value seconds per 1e6 plus time value microsecond, like that. Should be correct, right? Else, error exit, we do wrong input to get time, like that. Then here we get a mistake. Let's do return 1337. This is just to trick. I will never reach this line, right? Because I have my error exit, but this is giving me an error, so I just do this to trick that. So we have our chronometer. Thanks to get time of the day, we can get seconds, milliseconds, microseconds elapsed from 1970. That's what we're going to use to get the time in our simulation. So we go back in our dinner, and in our start of the simulation, we're going to call get time. That first of all, I have to copy in the other file, otherwise not use it. So and pass here. So we do table start simulation is equal to get time in millisecond. Okay, so after all the threads have been created, we do a chronometer check. We say, all right, the simulation now has started, and we set the bool to all threads ready. So our inner simulation here can, so in our dinner simulation here at the top, all the threads can move on this line. Okay, that's basically the idea by now. Then after that, we are going to join, wait for everyone. So wait for everyone. So I'm gonna reset I to -1, and I'm gonna call while I plus I is minor than table Philo number. Save thread handle. I want to call the join, so I do table Philos in position I access the thread ID and I pass it by reference. Then given that I want just to join the thread here, I don't need anything. I just pass null, and I join. So the cycle will be endless, but in the case all the philosophers are full, this is going to be important. Okay, so we need that point. If we pass over this line, if we manage to reach this point, this line, all philos are full. Okay. All right, let's go back in our dinner simulation and let's move on. Now, when we pass this line, the philosopher will start its actual simulation, right? So we need to set the last meal time, and then we start. So it's going to be while. The loop is not endless because it's going to be till the end simulation. We will see that we have a monitor thread that is going to check this. So here we can say while not simulation finished. We pass the table, so Philo table. Do you remember, right? In my getters and setter, we have this simulation finished, which basically returns in a thread safe manner the table and simulation boolean. So until the condition is not finished, until the dinner is not finished, what do we do? Well, first of all, the philosopher has to check, am I full? Because in that case, I exit. So basically we have something like if Philo is full, you just break the cycle, you finished. We leave it like to do thread safe. So we are gonna see if this variable is accessed only by the philosopher itself or also by the monitor. So maybe we have to change this access in a thread safe manner. So we just change with Philo full get bool. We are gonna use get bool and not directly Philo full, but here is just to get the point. Then the simulation, what is it? So we're going to call a function that I call it with the Philo. 3 is going to be sleep. So we can simply call our function use sleep, precise use sleep, and write that is sleeping. And 4th, we have thinking for think. So we will call a function thinking. We pass Philo to do. All right, we need a function to write the actual status of the philosopher. So write status, namely a function that is going to write the philosopher is thinking, is sleeping, is eating, and so forth, and a precise use sleep, because the real one is not precise, and we need to be more precise. So let's start by creating a precise use sleep function. We go back in our utils, and let's do that. So precise use sleep, the real one suck. Indeed, the use sleep is going to give us at least the time we ask, but very often it's gonna give us more because operating system lagging things, peculiarities, let's say. There are many details, but TLDR use sleep is not precise. So we're gonna do void precise use sleep. And as an input we take how much time, right? Use sleep, use sec. We also need access to the data which are in the table, because I want every time to check, is the simulation finished? Simulation finished. Because if it is the case, I don't want to sleep anymore. We have to go, we have to clean, and we're over. Okay, so the idea here is to use sleep the majority of the time, not CPU intensive. Then to refine last microseconds with spin lock, which is CPU intensive countries. Basically, the CPU is not released. So I'm gonna need a variable that I call start, and I say start is equal to get time in microseconds this time. Okay, then I'm gonna start a loop, I say while get time in microsecond minus start is less than usesec microsecond, right? So we get a start variable, which is the beginning of my loop, and then every time in my loop I get again the time, I subtract the start and I check if we already slept for the amount of time requested. Here, first of all, I check if simulation is finished. That's why we need the table. You just break, right? You don't sleep anymore. Then to make this hybrid, I'm gonna use a variable I call long elapsed, and I say elapsed is equal to get time again in microsecond minus start. Then another variable long, which is remaining, and I say remaining is equal to usec minus elapsed. All of these to get a spin lock threshold. What do I mean? Here I say if the remaining time is major than let's say an arbitrary variable, which is 1 millisecond, you just call the function uSleep, even though it's not precise. To usec, let's say divided by 2 to get a buffer, right? You're gonna sleep usec divided by 2 if we have more than 1 millisecond as a reminder time. You see, it's kind of tricky what I'm doing, but hopefully it is understandable. Else, it means that the reminder time is less than 1 millisecond. So if you have little time, you are gonna use a spin lock. Spin lock, basically you're keeping for yourself the CPU, and you do while the same condition as here at the top, copy, paste, spin lock, like that. Maybe this function as I did it is kind of confusing, but basically it's just an hybrid. I'm sleeping for the vast majority of the time. When I reach a certain threshold, which is 1 millisecond in our case, this is just a threshold. When this remaining time is less than this, I'm gonna spin lock. Otherwise, you're gonna call uSleep, okay? So this will give us precise or more precise sleeps than the actual system function uSleep, which is very often not precise. All right, so we have our precise uSleep function that we can use. So I'm gonna copy this and paste in my Philo.h into utils. Here it comes. Let's go back to dinner. So precise uSleep is done. Now we need a function that will write the status. Let's do that. Let's create another model. Write this time. The pattern is always the same. We include Philo.h. So we have to write the output in this fashion, like time in milliseconds, Philo ID, action, namely has taken a fork, is sleeping, is thinking, okay? We have to pay attention that this has to be done thread safe. So we need a lock. We go to Philo.h, and in our table, we create another lock. The table mutex is to read this data, right? On the contrary, table mutex write lock, just for the write, of course. It's called for consistency mutex, write mutex. All right, back to init. So we are gonna also init this write mutex, and now we can use it. Back to write, okay, write mutex. All right, let's do it. The function is gonna be void write status. Then we're gonna take again the status of the philosopher. You know perfectly well the pattern. We're gonna create an enum with all the states available. Philo states. So it's gonna be something like that, right? Another enum with all the states: eating, sleeping, thinking. Here I use take first fork and take second fork because this is gonna be useful for debugging purposes. And died. So we have all the states. Type Philo status. Okay, let's go back to write. So my write status is gonna take type Philo status. I call status. Then it's gonna take, of course, the Philo. So the idea is simple. We're gonna save mutex lock. So Philo table write mutex code is gonna be lock, and at the very bottom a lock. And in the middle we simply say if take first fork is equal to status, or take second fork is equal to status, and simulation is not finished. You see, this is important. Philo table bang here, not finished. What do? You call the printf, and you put your actual string. You say percent LD long digit, which is going to be the time. You're going to create a space of, I don't know, 6. We're going to do it left justified with this minus. This is just how the printf works. It has all these format specifiers. I'm going to do it white, the color, and then reset. So this is the timestamp in milliseconds. Then, all right, %d as taken a fork, new line. So I have these timestamps formatted and the actual string. Now at the very top of my function, I want to do long elapsed, which is the actual time, and elapsed is gonna be get time in milliseconds. Okay, so for every printf, I'm gonna use that, which is elapsed, and the second is gonna be Philo ID. Okay, so this is the thing, right? We have check the actual status. Then given the status, you're gonna print the milliseconds elapsed, the string, and so forth. So this is just a repetitive thing, right? There's nothing to really understand. The thing is that I want a write status, which is also in a debug mode. So at the very top, I'm gonna use a boolean, which is a boolean debug. And here I say, if debug is boolean, you call another function that I call write status debug, and I pass status, the pointer to philosopher, and elapsed, the time. Else we are gonna use this. Okay, important thing is that this has to be done at the very top. So I've wrapped around this logic, the locking and unlocking of the mutex, and then I will implement. Now this is pretty repetitive, there's no need to explain, I will show you the final result. All right, so this is the final result. As you can see, I have here at the top the locking and the unlocking, right? So all this code is like meshed inside the locking and unlocking, and it's pretty simple. In the case I want to debug, I'm gonna call this function. Now I will show you, otherwise you're gonna write normally. You see a lot of stuff because I have ASCII escapes, which make the thing quite cluttered. And the thing is that I have while not simulation finished call in every if. Arguably it is a better design to put if simulation finished at the very top and then just escape, but I don't know, in a multi-threaded environment this can happen at every time, so maybe it's better like that, I don't know, frankly. And the thing is that this function is not called all the times, right? It's gonna be CPU intensive because we have the short circuiting thing, right? This is gonna be called only if the first one is true, you see? So probably it is better to put at the top. Probably this is a better design, but nonetheless, it's not crucial. The thing is that all this stuff is wrapped around the locking and unlocking, and here at the very top I put if philosopher is full, you just return. This because when the philosopher is full, I just want to finish. I don't want to write anything. I want the simulation to stop. Okay. Now we're gonna check if we have to do thread safe. Thread safe with a get bool. We will see later when we're gonna create the monitor. Now let's see the debugging way. As you can see, it's a static function and it's basically the same. The only thing is that I have emojis. I have take the first fork, take the second fork. So now you understand why I have this specific enum to know what to do. And then I have for the eating, how many meals have been eaten by the actual philosopher. So I know I have a counter of all the meals taken. And when a fork is taken, I have the number ID of the actual fork taken, right? This is pretty handy for debugging purposes. And so the thing is that I have emojis and I know the fork that has been taken and I know the number of meals that has been done. All right, I'm gonna use a define in my philo.h like that. Define debug mode. By default is gonna be 0. So this is gonna be for the write function macro. Okay, that's the idea. All right, let's go back to our dinner, but before, let's copy this write status in my header. Here it comes. And now we go back to dinner. So now we have both write status and precise use sleep. So for the sleeping, what do? Write status is gonna be sleeping, philo, and here we use our macro, debug mode. And then we call precise use sleep, which is gonna be equal to philo table time to sleep. These are going to be constant values, so race conditions are not going to be an issue. And philo table, like that. So now let's implement the actual it function, which is the most important thing for a philosopher. So let's go up, it, routine. The idea is simple. We have grab the forks. So here having first and second fork is Andy, right? Second fork is Andy. I don't worry about left or right anymore. Then we have the actual eating, which is right, that you are eating, update, last meal, update, meals counter, and eventually bool full. Okay, 3, release the forks. Let's do that. So it's going to be a static void eat. As an input, we have a pointer to Philo, right? So let's do the first point. So safe mutex handle, we have to lock the first fork, so it's going to be Philo, first fork and fork, right? By reference, because my struct has also the ID. So here I need also to say explicitly I want the fork, I don't want the fork ID. And the opcode is going to be lock. We do the same for the second fork. Of course, in between we have to write the actual status, which is take first fork and take second fork. All right, that's it for the first step. Second step, actual eating. Now I have to set the last meal time, and I'm going to do it immediately. This is going to be a value that will be read also by the monitor thread. Every time it's going to check if the elapsed time between meals is major than time to die. So I have to do this in a thread safe manner. So I have set long. And here I want that every philosopher has an internal mutex that will be used with the monitor. Okay. So I need to give a mutex to every philosopher. We go back to philo.h and we give to the philosopher a mutex. So type mutex, philo mutex, useful for races with the monitor that we will create. You will see. All right, we go back to init, and for philo init, for every philo, we have to init also the mutex. So safe mutex handle, philo mutex. Operation code is gonna be, of course, init. Okay, like that. So now every philosopher is gonna have his internal mutex that is gonna lock and unlock to update last meal time. Let's go back to dinner, and I'm gonna set long philo mutex. Destination is gonna be philo last meal time, and the value is gonna be get time in milliseconds, right? Like that. Then we have to increase the meals counter, but this value is not gonna be checked by the monitor. It's gonna be checked by the philosopher itself. So I can simply increase normally. So philo meals counter ++, and then I simply write the status eating, the bug mode. Perfect. And of course I have the precise use sleep, which is philo table time to eat and a pointer to the table. Now I do an internal check if the philosopher is full. What do? I say if philo table number limit meals is major than 0, right? Because this is both a boolean but also a value. And philo meals counter is equal to philo table number limit meals. Well, in this case, it means that the philosopher is full. So we're gonna set bool. We're gonna pass the philosopher mutex. So philo mutex, the destination is gonna be philo full to true, right? All right, that's it. So you see that the eating phase is like that. At the very end, we just have to unlock the forks. Unlock. Now you can clearly see what I mean by take the forks. Basically, is locking first, second fork, writing the status, then eating, which is basically updating the last meal time, updating the meals counter, writing the status. So you see why the update of the meals is before the writing of the status, because of course I want to write the right number of meals, and then you just sleep for the amount of time requested. Then you simply check if we reach the full condition, namely the number of meals eaten is equal to the limits. If this is the case, we set in a thread safe manner the actual boolean true, and then we just simply release the forks. So this is the eat routine. All right. So eat is done. Now we still have to make the thinking routine. Let's do static void thinking. Take a pointer to the philosopher. And by now we just simply write the status thinking, and that's it. Then we will change some values because thinking is the only value that we can really model, because time to die, time to sleep, and time to eat are fixed. Time to think is the only one we can model to make the system more fair. All right, we think we already have a minimum viable philosophers project, and now let's try to launch with this input. As you can see, this is what is going on. We have all the threads that are writing stuff in the standard output. This is the normal, not debugging output. Here, if I change in philo.h, this is the debug mode to 1 and compile again, everything will change. You can see now that we have the meals consumed by the actual philosopher. We have some emojis, and we see the forks, right? We see the actual philosopher that has taken philosopher. For example, here we can see the output, and I can see one has taken the first fork, which is 0, and one has taken the second fork, which is 1, but it's not what I want. Let's go to init, and indeed there is a mistake here. Philo ID model 2, I forgot to put equal 0, of course, because I want the even philosophers to take the first fork. Let's try again. Okay, let's see. Let's say one has taken the first fork, which is the fork number 1, and the second should be 0. One has taken the second fork, which is 0. Perfect. Let's see, philosopher number 2, where is? Here it comes, has taken the first fork and the second, which is 1 and 2. All right, perfect. You see how immediately useful it is, this way of debugging, right? This output of debugging. Here you have the timestamps in white on the left. And now we have to keep going on with our dinner, because we need to check when a philosopher actually is going to die. To do that, we are going to need a monitor, right? We're going to need a monitor thread that is constantly searching for these dead philosophers. So before the start of the simulation, we're going to create our monitor thread. Here it comes, monitor. It's going to be safe thread handle. And of course, here I need a pointer to the actual thread. We're going to put inside philo.h our table, right? We're going to do p thread type monitor, like that. Is going to be the actual monitor thread searching for death. Now let's go back to dinner here, and I give as an input exactly that thread. It's going to be table monitor by reference. The function is going to be monitor dinner. Data this time is going to be the actual table, and the opcode is going to be create. All right, this is our monitor to do. Now let's create another file I call monitor.c or monitoring. So we include philo.h, and we are going to do void star monitor dinner void star data. We retrieve our table, so pointer to table is equal to pointer to table data, like that. At the very bottom we say return null, and here I'm gonna need another synchronization thing, which is that I have to be absolutely sure that all the philosophers are running before starting the controls. So I'm gonna do make sure all philos running. So I can say while not all threads running, a function that we will implement, and we will see the inputs to put. You just busy wait. So all threads running. This is another synchro utils. We're gonna do that. So we have monitor busy waits until all threads are not running. It's gonna be bool all threads running. And what can be the idea here? Well, we can have that at our dinner, essentially at this level. After wait all threads, we have synchro with monitor. We can increase a table variable counter with all the threads running. So let's do that. We go to philo.h, and we use a long that I call threads running number. Okay, then usual tedious thing, we go back to init, and we set this value to 0. Okay, now in the dinner, what we're gonna do, we're gonna actually increase this value. Basically, when every philosopher is gonna pass this spin lock, right? He's gonna start his simulation, and while he's starting, he's gonna increase the value of the number of threads that are running. So we say set long, but set long is not correct. We need another, which is increase long. Increase long. You're gonna lock the table mutex, so it's gonna be philo table mutex, and a pointer to the actual value, which is philo table threads running number, something like that. All right, so of course we have to implement. So very simple, we go in our synchro utils and we're gonna do that. So void increase long, and you take as an input a mutex, of course, mutex, and a pointer to a long value. The pattern is always the same, locking the mutex, lock, unlock, and just increase, say, at value plus plus, like that. Very silly function to increase along in a thread safe manner that I use specifically to increase the number of threads which are running. To synchro with the monitor. Okay, the monitor is gonna use these all threads running to indeed fetch this value and make the comparison if the number of threads running is equal to the actual total number of threads. So we're gonna implement all threads running. This function, let's say, is going to take a pointer to a mutex, of course, a pointer to the threads which are running, and the value of Philo number, we can say, Philo NBR, even though it is inside the table struct to make the code more readable. So we have to read the value. So bool return, we set initially return to false, and return ret. And in between, we have to actually read, right? We have to read, so I'm gonna lock and unlock. And here I say if at threads, the number of threads running is equal to Philo number, ret is equal to true. That's it. That's my all threads running function is, and what the monitor is going to use. So now we just copy these prototypes and we put in our header file, increase long as well. And now we go back in our dinner. So you get the point, right? In our simulation, every time we pass this first spin log, every philosopher is going to increase the number of the threads which are running. If you go to the monitor, we have while not all threads running that we just implement. The mutex is going to be the table mutex. The pointer on threads is going to be table threads running number by reference. And Philo number is going to be table Philo number, like that. Okay, so we managed to implement this function again. So my monitor waits until 100% all the threads are running before making all these controls. All right, spin locking. So this is going to be spin lock till all threads run. Then the actual thing, which is while, essentially like in our dinner. See here, go back. Every philosopher as while simulation is not finished. The same thing will happen with the monitor. I say while simulation is not finished. What do? You do your algorithm, basically constantly checking if the elapsed time of the philosopher not eating is major than time to die. Now we will implement this. So what is the idea behind this monitor? Well, this is simply like a referee. It's a referee that is constantly checking all the philosophers, right? It's gonna check the timestamp, right? Elapsed between last meal time. If this elapsed time is bigger than time to die, well, the philosopher is dead. And if this is the case, well, it's the end of the simulation. So in that moment, the flag end simulation is gonna be turned on and everything is finished. We have this referee. We have to implement this idea in code. Here at the very top, I need an iterator again, int I, and here I do I is equal to -1, and same thing while ++ I is minor than table Philo number. What do? You're gonna say, hey, if, then a function that now we will create Philo died, pass table philosophers plus I, right? This is pointer arithmetic. What do? You're gonna set the bool and simulation, taking the table mutex. So table and simulation, a reference to that. The value is going to be true, okay? And then you write the status, died. We pass the table philos plus I, the bug mode. That's it. That's basically it. Now we have to do the isDied function. And of course here, I want to stop the inner while loop and simulation is not finished again every time I check for that. Now we implement the isDied, Philo died function. So let's do static bool Philo died, and it takes a pointer to the actual philosopher. So what's the gist of it? Here we have to check last meal time, last meal. If this time is major than time to die, we set the return value to true. Okay, so I'm doing long elapsed. Then I will do the same long time to die just to not dereference too many times, make it the code clearer. So elapsed is gonna be get time milliseconds minus get long. We're gonna lock the philosopher mutex. So philo mutex, because here we have a concurrency between the monitor and the philosopher. Long value is gonna be philo last meal time. Okay, by reference. Time to die is equal to philo table time to die, like that. I just use this internal variable to not use this long referencing. And then what do? I simply say if elapsed is major than time to die, you return true. So the philosopher has died. Else you return false. Okay, like that. One important consideration here that we have to make is maybe the philosopher is full, so it's not died. He has simply finished its own simulation. So maybe Philo is full. So at the very top I say if get bool Philo mutex Philo full. You just return false because the philosopher has finished his simulation. It's clearly death, but not because the system is not working, but just because it has stopped its own stuff. Okay, let's go back to dinner and let's see what we still need to do. So we have wait for all threads, increase long so we can synchronize with the monitor. Just before that, here we need set time last meal. So it's gonna be Philo, or better, set long. Philo mutex. That is gonna be Philo last meal time, and the value is gonna be get time in millisecond, like that. Okay, so we're gonna set the last meal time. This is an important value. Then we increase the number of philosophers, and then we get into our simulation. Eat. We have eat, sleep, and think. All right, let's go back to dinner start here at the very bottom. We still have to handle one philosopher, so we're gonna do a function that I call lone philo, or better, I'm gonna create another thread just to make it more real. So save thread handle. I take table philosophers in position 0 this time. Thread ID function is gonna be lone philo. Data is gonna be the philosopher. Table philo in position 0 by reference, and then I simply create this big boy. All right, so we have a thread for a lone philo. We create the function lone philo. It's gonna be the same algo and as the normal philosophers, just we're gonna do some changes. We're gonna fake to lock the fork. Sleep until the monitor will bust it. Will bust. Okay. So as usual, void star lone philo void star arg. We retrieve the philosopher, a pointer like that. Then same, wait all threads. So philo table like before, even though it's only one. Set long philo mutex philo last meal time, get time in millisecond. Like that. We increase the number of threads that are running, so our monitor is ready, is able to go. Then I write status, take first fork, even though I'm not taking, this is just for output purpose. So we are faking to take the actual fork. And then I simply say while simulation finished table, while not simulation finished, you sleep for 200 milliseconds. Okay, I can use sleep, I don't really care. At the very bottom, we put return all. So basically, the lone philosopher is like a normal philosopher. The only thing is that he keeps sleeping for 200 milliseconds until the monitor will bust him. We'll find him, because the last meal time is never going to be updated eventually. But let's try to compile and see what do I mean by that. So let's launch with one philosopher. Is not working. It's an infinite loop, allegedly. So there must be an issue.
A few moments later.
The problem is here, I guess. Time to die. The thing is that I converted time to die at the very beginning, right? When we have initted, you remember? When we were parsing at the very bottom here, time to die was already converted to microseconds. But here I got it wrong, because here we are doing milliseconds. So time to die divided 1e3, like that. And as you can see, it works, right? Now I have a little mistake, but doesn't matter. So we have the first philosopher that is taking the fork, and after some time, for example 1 second, has been busted by the actual monitor thread. That's the thing I wanted. So pay attention here that time to die convert back to milli. So let's try to launch with 5 mils. We get something like that. Now we get this bug, but we don't really care. The thing is that, as you can see, we have philosophers that are doing 5 mils. 3, 1, 4, 2, you get, right? Then let's try to check if the monitor works. As you can see, it finds a dead philosopher given the timestamps. Let's try 300. Okay, it seems like it's working. And now let's refine our code. Going back to my dinner start, if we manage to reach this line, as we said, it means that all the philosophers are actually full. So here we can say set bool table mutex, table mutex, table and simulation to true, right? We can set the end simulation to true, and this time the end of the simulation is not gonna be set by the monitor, right? This is going to be set by the main thread, because this is the main thread. It is not the philosopher thread. It's the main thread, the one that is launching all the philosophers. If we manage to read this line, is because we have crossed this join, namely all the philosophers have finished their own simulation. So we set this to true. Why is that? Well, because also the monitoring is waiting for the simulation finished, right? So it is a double way, right? You get my point. The simulation finish flag can be turned on by the actual monitor, or by the main thread is gonna turn on this thing. Hope this is clear what I'm saying. So let's go back to dinner. So after that, we are gonna join also save thread endo. We're gonna join also our monitor. So table monitor, because the join is not only waiting for a thread, but it's also cleaning resources. This is useful for not having leaks. Okay, so I'm gonna join also this. Then we go back in our main, and we have to create our clean function that is gonna clean everything, right, with no leaks. We put this in our utils clean, and we take as an input a pointer to the actual table. Let's do that. We also have to clean all the stuff inside the the philosopher. So I'm gonna do type Philo, pointer to Philo, and an iterator. I is equal as always to -1, and I say while ++I is minor than table Philo number. Philo is equal to table Philos plus I, and here I had to destroy the mutex of the philosopher. So save mutex sendle Philo mutex operation code. This time is gonna be destroy, like that. Then I do the same for the table mutexes. So save mutex handle is gonna be table write mutex and table mutex. And then I'm gonna free the forks and the philosophers. Table forks, free table philosophers. That's it. That's the clean function. Destroy the mutexes and freeing the actual malloc elements. Then I'm gonna copy these and put my header. And now we have our beautiful clean function. So we can cancel this. Now let's make some tests. Okay, this works. Now with this we have that nobody should die, right? On the contrary, I have that some philosophers are dying. What is the problem here? All right, this doesn't work. In this condition, philosophers shouldn't die when they are 4. There is a bug lurking somewhere. Let me find out.
A few moments later.
All right, it seems like I found a bug, which is this one. I call useLeap not on RAM remaining, but on useLeap again. This, of course, bug spotted. You probably see that this happened immediately, right? I will cut all the silences and all the bestemmie for Italian friends. But this took a lot of time, like all the times, these silly mistakes. So let's try now. And as you can see, it works. The system keeps up. Even though I have many applications open, it seems like to be alive. The thing I want to show you is that when we have an odd number of philosophers, like for example 5, here the system should keep running indefinitely, but sometimes can not run. And now I will show you the reason. First of all, let's go to phil.h and let's change the debug mode to 0. I'm gonna compile again and launch. So we're gonna get a normal output. And as you can see, I'm gonna copy this And I'm going to put in this marvelous website, which is Philosophers Visualizer, that is going to show you exactly what is going on. Now you see the problem on end. We have one philosopher that is thinking too long, is thinking for too long, and we have a philosopher that is not thinking at all. We have some philosophers that are just eating straight off the thinking phase. So I want more control over thinking. I want more control. I want the system to be more fair. So as you can see, for odd philosophers, we have this system which is not fair. Not fair, it means that not every philosopher is going to respect its own turn. Now, I'm going to discuss with you some my observations that I've made on the dining philosopher problem. This can be wrong, frankly, I'm not totally sure, but these are just some empirical observations. We discussed this together. So when we have an even number of philosophers, I've noticed that when time to eat is less or equal than time to sleep, there is no thinking time. Namely, the symmetries of the system imply that there is no thinking time. Thinking time is the contention time, is the time spent waiting for the forks, right? But in a system when we have even philosophers and time to eat is less equal than time to sleep, there is no contention at all. As you can see, right? The symmetry of the system implies that there are no time to think at all. Just watch the first case. Every time when a philosopher finishes to sleep, can immediately start to eat because the neighbor is sleeping, namely the neighbors, right? Both neighbors are sleeping. Still holds true for when the time to sleep is equal to time to eat. We have a perfect symmetry of the system, you see? Immediately eat, sleep, eat, sleep, eat, sleep. There's no need for thinking time. The thing is different when the time to eat is measured than time to sleep. As you can see in this case, right? We have 200, 100. And in this case, time to think is equal to 100, forcefully by the system, by default, right? The system implies that it's necessary to have 100 thinking time. So we can say that the thinking time exists in a system when we have an even number of philosophers, when time to eat is major than time to sleep. This is not true, on the contrary, when it's minor equal than time to sleep. So now I will try to show you why when the system is even, when we have an even number of philosophers, I don't want to control the thinking time. This is going to be done by the actual symmetries of the system itself. Let's pretend we have a big sleep time, which is still minor than time to eat, right? What is going to happen? When a philosopher is going to finish to sleep, it's going to wake up and it's going to try to reach for forks, but it cannot immediately reach a fork because it's blocked by the neighbors, which are still eating. Namely, the forks are locked, right? The philosopher simply cannot eat by the symmetries of the system after he has finished to sleep, okay? Forcefully, there is some thinking time in a theoretical scenario, right? If the system works smoothly, perfectly. Same holds true if the sleeping time is very little, right? When the philosopher is going to wake up, he's going to still find the neighbors eating, so the forks are going to be locked. So TLDR, for even philosophers, the system is already fair because no philo can eat 2 times in a row, you see, because it's blocked by the neighbor, by default, by the system design, by the system architecture, if you want, right? Now let's watch this for odds philosophers. We get this. For odd philosophers, for example, 3, 800, 200, 200, when time to eat is equal to time to sleep, we have time to think, which is equal to time to eat or time to sleep. Just watch the images. You can see very clear what is going on, right? When I have time to sleep, which is major, what is happening? We have that time to think is equal to time to eat per true minus time to sleep. Time to eat per true this time because we have to wait for our neighbor to finish eating when we have odd philosophers. We don't have a perfect symmetry. So look here, when we have 200 time to eat, 300 time to sleep, we have 100 time to think. And when we have 200, 400, we get 0, right? Time to think. And when we have 200, 350, we have 50 because 200 per 400 minus 350, 50 milliseconds to think. Again, this is stuff mechanical, right? It is implied by the system itself. So this is when time to eat is major than time to sleep. We have the same thing. When we have 200 and 100, we get 300 milliseconds time to think. And as well, when we have 250, we get 350 milliseconds. So what is the take-home message? Well, if philosophers are odd, we get that time to think is equal to time to eat per true minus time to sleep, right? In every case, even in the first case when the values are equal. So in this case, in the first, we have time to think is equal to time to eat per true minus time to sleep. You just have a visual understanding here thanks to the marvelous philosopher visualizer. Now, why all this story? Well, we want to control when philosophers are odd the thinking time, because we can have that one philosopher can actually eat immediately after he has slept. In this case, if we don't control. Just watch this combination. We have the second philosopher that eats, sleep, and then goes to think. The third eats, sleeps, but doesn't go to think. Immediately starts to eat, making the system not fair and making the system not working. The second philosopher is going to die, even though in the system shouldn't die. So let's have a visual understanding of what I'm saying. It's pretty weird, right? I think it's pretty complicated. So let's say we have philosopher 3, 800, 200, and 200. And let's start the simulation. So initially we get philosopher number 2 that is locking fork number 1. So philosopher number 1 is blocked, right? Because the fork is locked. And then we have philosopher number 3 that is locking the lock number 0, the fork number 0, but philosopher number 2 has locked the fork number 2. So even philosopher number 3 is locked, right? You see the image up here, I think it's clear. So now philosopher number 2 can eat, and that's what he's going to do. He's going to eat, right? Then he's going to release the forks. Then what happens? We have that philosopher number 1 is going to lock his fork, but the other fork is already locked by philosopher number 3 that is going to lock the other fork and is going to eat. In this time, philosopher number 2 is sleeping, right? Philosopher number 3 is eating, like that. Then philosopher number 3 is going to release the forks. And finally, we get that philosopher number 1 is going to lock the fork, okay? Philosopher number 2, pay attention here, has finished to sleep, but is forced to think by the system, you see? It's forced to think because philosopher number 1 has locked the fork. So philosopher number 1 is eating, philosopher number 3 was sleeping. Now, what is going to happen? Philosopher number 1 released the forks, and now what is going to happen? What do you think? What if here number 3 is faster than number 2 to take the forks, right? Because of the system possible conditions, we are in a random area. It's the operating system scheduler that is going to orchestrate everything. So let's pretend number 3 is faster. What he's going to do? He's going to lock both forks, as you can see, and he's going to eat. He's going to eat again, forcing number 2 to think another time. Right? Because there is no control, right? There is no control on the thinking. And I want to act exactly here. I want to avoid this kind of scenario. Double thinking. The system is not fair. This can work, but in practice won't. I mean, the system can work. It can run, but at times you will get this scenario. So we are gonna forcefully control the thinking time. A more robust solution would impose a thinking time if available. So we're gonna think, is there some thinking time available? You saw the formulas. If it is available, we're gonna think for a custom thinking period that you will see in code. So after sleeping, every time a philosopher is forced to think a little bit. This is my solution to the dining philosopher's problem. I don't know if this is correct. I don't know, but thinking is the only variable in which we have control of. So here, just before entering the loop, I want to desynchronize the philos. Basically, I want to make an even or odd philosopher wait for a custom amount of time just to have a perfect synchronization while starting. This will help in fairness. So for even philosophers, I will have a micro waiting, milliseconds waiting, just to desynchronize, avoid too much for contention. If the system contains odd philosophers, we're going to start by thinking. Now you will see what I mean in code. I think would be easier. The function is the synchronize philos. It takes philo as an input. We are going to implement this, and we're going to put this in synchro utils. So this is a function make the system fair, trying to make the system fair. All right. So it's going to be void the synchronize philos, a pointer to the actual philosopher. And I say if the system contains an even number of philosophers, so if philo table philo number model true equals 0, else it's an odd system. What you want to do, you just want to make a philosopher sleep for if philo id model true is equal to 0. We're gonna make the dude you sleep for let's say 30 milliseconds. 30 milliseconds because it's half the time of the minimum time available that we can give to the system, right? Which is 60 milliseconds. So it's going to be 3e4 table. Else, if the system is odd, I'm going to say if Philo ID model true, we are going to start by thinking. So this is a function that now we have to create very well. I don't remember if this is static or not. So we go back to dinner, we remove the static, delete word, and we put this into philo.h. We say fairness. So synchro utils thinking takes as an input philosopher. Okay, so let's elaborate my thinking function given what we have talked about. Immediately I say if philo table philo number model true is equal to 0, you just simply return. First of all, of course, you just write the status. So we just so if the system is even, we don't care. We don't care. Quick refresh, right? If we have a time to eat minor equal, we don't have thinking time. If we have time to eat major, then time to sleep, we have a thinking time. But as we saw, the system itself will take care of the fairness of the system, right? Because the neighbors are going to be eating. So I don't care. The system is already fair. I don't care. System already fair. Now, odd. There can be scenarios in which not fair. Not always fair. What do we do in this case? First of all, I want some local variables here, which are time to die, time to eat, and time to sleep. I don't want every time to fetch with the proper notation. To sleep, time to think. Okay. Time to eat is equal to philo table time to eat. Time to sleep is equal to philo table time to sleep. Time to think is equal. We just saw previously, right? In an odd system, what is time to think? Just watch the images here. The formula is clear, is time to eat per true minus time to sleep. Of course, in an ideal scenario, I'm talking about an ideal scenario. So given that, we're gonna just plug this formula inside time to think. So it's gonna be time to eat per true minus time to sleep. This is the possible time to think, available time to think. Let's say that. Available. Of course, this value can be also negative, right? In this case, we say if time to think is minor than 0, of course, doesn't make any sense to have time to think negative. So you say time to think is equal to 0. On the contrary, you're going to say, here's where the precise control I want to make on Phil. It's exactly here. I'm going to say precise you sleep, and I'm going to say you are going to sleep. Time to think, which is the time available, not all the time, but I'm going to say, for example, per 0.42. Forcefully, I'm going to say, at least you, philosopher, you're going to think 42% of your thinking time after you wake up. This is an attempt to avoid a philosopher eating 2 times in a row. I hope you understand what I'm trying to do here, right? We are in this moment in which philosopher number 3 is faster than philosopher number 2. And is going to eat again, forcing number 2 to think again, making the system not fair. Being smart, we are going to force the philosopher number 3 to think for some time, giving time to philosopher number 2 to take the fork and making the system more fair. That's what I'm trying to do. And then we leave the 58% of the time to the actual system itself to take care of itself. Now, one thing that I want to do is to change this thinking. I want to put here also a boolean. Now I will explain you why. Here I'm going to put false. On the contrary, just before. So let's change the prototype. So here I change the thinking just for output reasons. I'm going to put a false there. I'm going to change the fill.h. Thinking is taking a bool. The core pre-simulation. Because the first time I call thinking is just before the simulation actually starts. And I don't want to write in the standard output that philosopher is thinking. It's just for synchronization reasons. So we go back to dinner. So here is false. Here I have desynchronized philos, but in synchro utils, you put here true. Okay. Then we go back in thinking here at dinner, and you say if not pre-simulation. Here we just add the boolean bool pre-simulation. You write the status. Okay, as simple as that. Just a minor thing, but that's it. Let's try now to launch this code. So it's going to be 5, 800, 200, and 200. And as you can see, this time having a refined control over the thinking period just after the sleeping. Namely, I've used 42. Empirically, it seems like the 42 is working. It's just a magic number, as you may guess. 42, no specific reason to do that. I just want to say, hey, when you finish to eat, just wait a second. Just think, let the system self-synchronize and do its own stuff. Okay, let's try with 4. There should be 400, 200. Of course, this is gonna die because we don't have enough padding time. Let's do 410. As you can see, the system works, even though I have many applications open. So there are many threads running around inside my computer. It seems to work properly. If we have an unfixed number of meals, for example, 5, it works. Let's just change here the debug mode to 1, so we can have a better appreciation of the output. Let's do again 5. As you can see, every philosopher has taken 5 meals and then has finished his thing. Let's do this case. In this case, a philosopher should die. And overall, it seems like everything is fine. Okay. All right. This has been pretty long, arguably complicated. I don't know if the solution is 100% correct. This is just my implementation. I will push all on GitHub, so maybe you can check further this thing. Hopefully this was useful. And yeah, thank you very much for watching, my friend. Enjoy.